Hello, everybody, and welcome to the final episode in this series. This episode is a continuation of episodes 3.1 through 3.3 and will introduce the concept of multi-period planning. If you haven't seen the previous episodes, please check them out by clicking on the link in the video. And before we get started, please don't forget to hit the subscribe button below. Let's start with a quick overview of what multi-period planning means. Multi-period planning deals with problems spanning multiple distinct time periods. These time periods can vary in duration and number. The decisions in each time period are affected by the constraints and bounds placed on the problem in all time periods. Constraints, bounds, and parameters can either be static, also called time invariant, or dynamic, also called time variant. This means that some inputs will change from period to period while others will not. This is all to say that multi-period problems are markedly more complex both in formulation and in analysis. In today's episode, we will pick up where we left off in episode 3.3 and introduce the problem in the context of 4 production periods. As with past episodes, we will start with the problem description. RMC Incorporated is a small firm that produces a variety of chemical products. In their production process, 3 materials are mixed together and heated to 300 degrees Fahrenheit to produce 2 products, a fuel additive and a solvent base. Each ton of fuel additive is a mixture of 0.4 tons of material 1 and 0.6 tons of material 3. A ton of solvent base is a mixture of 0.5 tons of material 1, 0.2 tons of material 2, and 0.3 tons of material 3. There are multiple markets for these products, however, the demand and pricing varies. After deducting relevant costs, the profit contribution in premium markets is $44 for every ton of fuel additive produced and $38 for every ton of solvent base produced. For discount markets, the profit contributions drop to $15 for every ton of fuel additive produced and $20 for every ton of solvent base produced. RMC has 2 mixing units available for production of fuel additive and solvent base. These mixers operate 6 hours a shift, 3 shifts a day, 7 days a week. Both units can mix solvent base or fuel additive. The newer mixer 1 rate is faster than that of the older mixer 2 unit. While materials 1 and 2 are procured solely from vendors, material 3 is an intermediate product that can be manufactured on site or procured from vendors. On-site manufacturing requires utilizing 2 flashing units to produce material 3, which is a stabilized version of material 4. The flashing units operate by heating material 4 and then flashing it under pressure to remove volatile compounds and stabilize the material. The volatile compounds are a byproduct, and RMC pays a small fee for a local power generation facility to incinerate this gas in accordance with local environmental regulations. The flashing units operate 6 hours a shift, 3 shifts a day, 7 days a week. The vendors supplying material 3 have limited availability and offer significantly different pricing. The planning department is working to determine the production and inventory plans for the next 4 weeks. Below, we have a depiction of this problem. We have our material 4, which is fed to our flashing units FD1 and FD2 to produce a byproduct, which is sent offsite for processing, and our material 3. Materials 1, 2, and 3 are then sent to either mixer unit 1 or mixer unit 2 in different proportions to produce either a solvent-based product or a fuel additive product. We're now ready to talk about the problem definition. However, because I'm going to be reviewing a lot of the details spelled out here in the data later, I'm going to skip this and jump down to the objective or the opportunity statement and model development. Our opportunity statement is the same as it has been before. We're going to maximize profits by determining how much of each product, solvent base and fuel additive, to produce with an existing equipment capacity and with the raw materials available for each time period. One new addition to the opportunity statement is that we also have to manage our inventory around planned unit outages and supplier interruptions. With that, we're ready to move on to model development. I'm going to cover the specific definitions and parameters first, and then move into the mathematical model. Over here on the left, we have F and S, which we're going to let define our fuel additive and solvent-based products. We have M1, 2, 3, and 4, which represent our raw materials, material 1, material 2, material 3, and material 4. B1, which is going to represent byproduct 1. RX1, RX2, which represent our product mixers 1 and product mixer 2. And FD1 and FD2, which represent our flashing units 1 and 2. I is going to represent a set of all products that we manufacture, which is going to include S, F, and M3. J is going to represent a set of raw material inputs for our processes, which includes materials 1, 2, 3, and 4. S is going to represent a set of suppliers from whom we can procure additional material. In this case, we're going to be using 2 suppliers, supplier A and B. And Z represents a set of all byproducts produced through our manufacturing processes, which in this problem is only B1. K is going to represent a set of processes or equipment that we use to manufacture our products and materials. This includes RX1, RX2, FD1, and FD2. And N is going to represent the various time periods that we're using in our planning. So we have 4 time periods for this problem, 1, 2, 3, and 4, which from the problem statement represent weeks 1, 2, 3, and 4. Over here on the right, we have our parameters. So P sub Ni is going to represent the profit of product I in period N. So this is a time variant, or could be a time variant parameter, as we discussed earlier, because we are now indexing this over the various time periods. C sub Z is going to represent the cost of byproduct Z. So you can see we do not have N here as a subscript, so this is going to be a time invariant parameter for this specific problem. Y sub Nik is going to represent the amount of product I manufactured by process K in period N. D sub Ni is going to represent the maximum demand for a product I in period N. W sub Nz is going to represent the amount of byproduct Z produced in period N. Q sub Njs is going to represent the purchased material J from supplier S in period N. X sub Ij is going to represent the material J consumed per ton of product I made, and this is going to be time invariant. B sub Zi is going to represent the byproduct Z produced per ton of product I, and like X sub Ij, B sub Zi is also time invariant. R sub Njs is going to represent the rate for material J from supplier S in period N, and A sub Njs is going to represent material J availability from supplier S in period N. M sub Nj is going to represent the inventory change for material J in period N. So this is a newer variable. So M sub Nj is now going to represent whether we build or draw a specific material from inventory in a given period. I sub Nj is new, and it's going to represent the actual inventory level for material J in period N. And V sub J is also new, and it is going to represent the maximum inventory for material J. So the maximum allowable inventory we can have on site and stored in a tank at any given period. So this limit here, or this bound, is time invariant. T sub Nk is the time available for process K in period N, and R sub Ik is the production rate for product I on process K, which is also time invariant. So with that, we're ready to build the mathematical model, and we'll start with the objective function. So here we have our profit equation, and there's 3 terms to this equation. So this first term here is our profit contribution. This is the profit of product I in period N times the amount of product made on equipment or process K in period N. And that product is going to be summed up for all products I, all pieces of equipment, processes, or machines K, and across all time periods N. These next 2 terms are actually deducted from the profit, so these are negative contributions. This is C sub Z, the cost of byproduct Z, multiplied by W sub Nz, the amount of byproduct Z made in period N, summed up across all different byproducts across all periods N. And here we have the cost of material J from supplier S in period N, multiplied by the amount of material J procured from supplier S in period N. So R sub Njs multiplied by Q sub Njs, summed up for all suppliers, all materials, and all periods. And so you can see that our objective function here looks very similar to what we did in episode 3.3, but we have now an additional index to sum everything up over, which is the time periods N. For our decision variables, we have Y sub Nik, which is the amount of product I that we're going to manufacture by process K in period N. W sub NZ, which is the amount of product Z produced in period N, byproduct Z produced in period N. Q sub NJS, which is the purchased material J from supplier S in period N, and a new decision variable, M sub NJ, which is going to represent the inventory change for material J in period N. So M sub NJ, unlike our other decision variables, can actually be negative. So we'll see that when we define that below in the Python code. But we can either make a decision to draw material from inventory, or we can make a decision to build inventory. So if we needed to maybe procure this material in an earlier period for use in a later period, M sub NJ would be positive. For our constraints, we'll start like we have in past episodes with our material balance constraint. Here we have X sub IJ, which is again the amount of material J consumed per ton of product I, multiplied by the amount of product I made on machine K in period N, and that gets summed up across all I, all products, and all machines K that make product I, to give us the total amount of material J consumed in a given period. And that has to be less than or equal to the amount of inventory change of material J in period N. So this is, again, if we're going to draw inventory or draw material from the tank, this makes our availability go up. But if we decide that we're going to make this negative, then this is going to, on the right-hand side here, is going to reduce the amount of material available. In addition to the inventory change, we have to look at the amount of material J being produced on process K in period N. So if this is a intermediate product that has an upstream process to produce, we're going to sum up how much of that we're manufacturing on site across all machines that make it. And then, of course, this last term here is the amount of material that we're going to purchase from supplier S in period N. So this right-hand side term basically is your inventory change plus whatever you're making on site or in your manufacturing upstream processes, plus anything you're going to procure from a vendor. And this left-hand side, which is the amount you consume, has to be less than or equal to that. And we're going to replicate this material balance for all NJ. So for all materials J in all periods N, we're going to have a material balance. We also have now a new constraint, which is an inventory balance. So I sub NJ represents, again, the amount of inventory of material J we have in period N. And that's going to be equal to the previous period's inventory, so I sub N minus 1J, plus the inventory change in this period, M sub NJ. So if we had 100 tons in period 1, and we decided to use 20 tons in period 2, we know that I sub NJ would be 100 minus 20. And we're going to make this inventory balance for all materials J and all periods N. Now, I will point out that you could simply have moved this inventory balance into the material balance via substitution. However, I am breaking it out here because, as we will see later when we do sort of analysis and reporting, sometimes breaking these out into distinct groups makes that easier. Our byproduct constraint, so B sub ZI, which again is the amount of byproduct Z made per ton of I, multiplied by the amount of product I made on machine K in period N, summed up for all machines making product I and all products I, we get our total byproduct. And that is, again, set equal to the decision variable W sub NZ. So we're really sort of constraining this. And we're going to do that for all byproducts and all periods N. For production time, we have Y sub NIK, the amount of product I made on machine K in period N, divided by R sub IK, the rate at which we can make product I in machine K, and that dividing R into Y gives us our time that we use on that machine or process, summed up across all our products, gives us, has to be less than or equal to the time that we have available on our machine K in period N, T sub NK. And we're going to do that for all combinations of N and K. Our product lower bound, so this is simply stating that all of our decision variables for making product I in machine K in period N have to be greater than or equal to 0. We can't have negative production. And we do that for all NIK. Our product upper bound is going to be Y sub NIK, the amount of product I made on machine K in period N, summed up for all machines. And that has to, and that's going to be our total product I made, has to be less than or equal to the actual demand for that product I in period N. So total product I made in a given period has to be less than or equal to the actual demand that exists for that product in that period. And we're going to make this constraint for all products in each period. Our byproduct lower bound, similar to the product lower bound, just says that we can't have a negative production of byproducts. So that all of our W sub NZ decision variables have to be greater than or equal to 0. We have our material upper bound. So this is a supplier constraint. So it says that Q sub NJS, which is the amount of material J procured from supplier S in period N, has to be less than or equal to the actual availability of material J from supplier S in period N. So we can't just buy as much as we want. We can only buy up to what's available from that supplier. And we'll do that for all NJS. Our inventory lower bound. So we have tanks that contain inventory. So we know that I sub NJ, the amount of inventory J in period N, has to be greater than or equal to 0. Obviously, we can't have a negative inventory. And we'll do that for all NJ. And finally, our inventory upper bound, which is I sub NJ, has to be less than or equal to V sub J for all NJ. So we can never build or purchase more material to put in a tank than we have room for it. So we are constrained by V sub J. So we're ready to get into the Python code. And as we've done before, we are going to import our needed libraries first, which includes pandas, NumPy, and pulp. We'll do that. And then we're going to read in the data from our data set. And I'm going to pause here, and we're going to open the data set, and I'm going to go through the data in a little more detail than I have in the past, because I want to highlight how to set this up for a temporal problem where we're looking at multiple time periods. All right, we have our data here, and we're going to start with the products tab. So this tab includes information on the product, the price, the minimum and maximum demand. You might use minimum demand if you say have a contract that says you're going to provide a specific customer or market a minimum amount, but for this case, we don't have any of that. And then the maximum demand, which is what the market will bear in terms of buying your product. The tier, which indicates whether this is a premium or a discount market, and then the period in which the supply is. So here we have product F at $44 a ton with a maximum demand of 50 into the premium market in period 1. And then the next row, we have product F at $15 a ton, the maximum of 15 tons of demand. This is a discount market or tier 2 market in period 1. And you can see that we are, for the sake of simplicity, introducing this concept, assuming that our pricing does not change and our demand levels do not change for these products and markets for each time period. So what we ended up doing was just replicating these records for each time period 1, 2, 3, and 4. We did the same thing for S. So again, $38 for product S in a premium market up to 75 tons maximum demand, $20 a ton up to 25 tons of demand in the discount market or tier 2 market, and that's going to be the same for each of these periods for each week. And similarly for M, which is an intermediate that we do not sell, we don't have a price for it. There's no maximum demand, there's no market for it, so there's no distinction on the tier 1 or tier 2, but we do have this being produced, potentially being produced within each time period 1, 2, 3, 4. So that's how we set the products table up for multi-period planning. There are other more elegant ways to do this. You could have a start and an end date here and do some data transformations to then create the distinct periods from a specific time period duration and then a start and end date. But to illustrate the concept, I've made this a little bit more explicit. For materials, right? So this tab has our material list, the available material. This can be read as opening inventory or what material we have on hand at the beginning of our planning period. The minimum inventory, so this might be like what's referred to sometimes as like a safety stock. So maybe we have supply reliability issues from our vendors, and so we always want to keep some sort of minimum inventory on hand. You could constrain the problem to make sure that you never draw your inventory below this level. For, again, simplicity and introducing the concept, our minimum inventory is 0. And for each of these tanks that contain materials 1, 2, 3, and 4, we're going to assume they're all the same size and they can all hold up to a maximum of 200 tons of material each. And this again is time invariant information, so we don't have to make any sort of distinction here on period. This is our purchase table, so I'm going to zoom in here a little bit. So our purchase table is actually represents essentially the supplier information for each of our materials. So in column A, we have material 1, 2, 3, and 4. You've got your supplier that material is coming from. So we can see for materials 1, 2, and 4, we only have one supplier, A. But for material 3, we have two suppliers, A and B. Column C is the maximum amount of material that we can buy from those suppliers. So for materials 1 and 2, we have 15 and 10 tons, and then we're actually going to keep that the same throughout the entire period. So from supplier A, for materials 1 and 2, regardless of period, the price and availability is going to be static. That's also going to be true for material 4, which is going to also be static. So the price and the availability is going to be the same for material 4 in each period. For material 3, we're going to do something a little different. So for material 3, you'll see that for the first few periods, we actually have static data. So suppliers A and B, the amount that we can procure from each supplier and the price at which we can do it is going to be static for periods 1, 2, and 3. But in period 4, we have heard from our supplier B that they're going to have a planned outage at their facility or their distribution center, and so they will not be able to supply us with any material 3 in period 4. So in period 4, we see that we have a pretty big deficit of available material. So 58 tons can be procured in each of these earlier periods, but in period 4, we'll only have 8 tons that we can buy from supplier A. Our recipe file also has not changed. This is again the X sub ij, right? This represents the amount of material consumed per product in column A, material in B, and then the consumption coefficient in column C. This is static and time invariant, so no distinction on time period here. Byproduct table. So again, this gives us the cost of our byproduct. So B1 has a small cost to it. It's pretty, insignificant. It's what we pay to have it sent off site for processing. Unit rate. So again, this is also a static table, time invariant. So we have our units, and we have the products that can be made on each of those units, and the rate, tons per hour, that you can make or produce these specific products on those different machines, processes, and equipment. And that does not change with time. And then we have our final table, which is unit capacity. So in column A, we have the unit. We have the time available that unit can be operated or run or used for manufacturing in column B, and the period that is associated with. So in period 1, we can see that both our mixers, RX1 and RX2, and our flashing units, FD1 and FD2, are available for 126 hours, so 100% availability in period 1. That's also true for period 2. It's also true for period 3. So for all 3 periods, all of our processes are going to be fully available. But in period 4, we find that we have some planned maintenance that needs to be completed on our flashing units. They have to come down for some, let's say, maybe some inspection. So they will not be available. So there's going to be 0 hours of operating time available for flashing units 1 and 2 in period 4, but our mixers will be still 100% available in period 4. So again, this data is very similar to what you saw in episode 3.3, but where we've had to show a time dependence on some of these variables like capacity or product demand and pricing or material availability and pricing, we've indicated that now with an additional piece of information on the period. So with that, we're going to jump back and walk through the Python code and solve this problem. Okay, so we have imported our libraries. Now we're going to read in all of our products from the data that we just reviewed. We bring in each of those tables. And now we're going to do some basic data transformation. So the first one is with this DF products table. Because we have a product and a market, tier 1 or tier market, and a period, we're now going to essentially create a unique variable for each period. So we do this essentially by creating a new column called var, which will represent the unique variable name, which is basically just going to be the variable and the market. So F_1 would be fuel additive in the premium market. That's going to be one of our variables. And so we'll do that for each time period. So over here on the right, you'll see these two columns, which is our period column, and then the specific variable name for creating, which is a combination of the product and market. The next one is DF materials. There's no data transformation required for that. We can bring that in directly as is. But from that DF materials table, we will create later on a dictionary that we'll use for doing our constraints on inventory. We will use this opening inventory information, and then also we'll bound one of our decision variables with this maximum inventory information. We bring in our DF, or we do transform our DF recipe table. So we create a yield table from that. And so essentially what we're saying here is that we want to create a yield table for our byproducts. So this table looks at the DF recipe table, looks at for any consumption coefficients that are negative, representing a byproduct. And we're going to go ahead and merge that with our DF products table to get a new table called DF yield that has the product that is tied to the byproduct material. So this is saying, hey, we make B1 as a byproduct every time we produce a ton of M3. And then the consumption coefficient, which we know from the recipe table, but we have to create it for each unique time period. So even though this consumption coefficient is not time variant, we just create it for each time period, and you'll see later why we do that, because it makes building the bounds and everything else easier. Next, we have the DF recipe table. This time we're only looking at the positive consumption coefficients, so we can do the material balances on each of our materials consumed. So materials 1, 2, 3, and 4. So we go through some data transformations, we filter out the byproducts, then we take our DF recipe, we also merge that with products so that we can link the material consumed with the product that we're talking about. And so again, you can see here, and we're gonna, because we have multiple periods, we're gonna end up dropping duplicates and then sort this. But you can see what we end up with is a final recipe table that has our product, the material consumed for that product, unique product name, so S_2, and the consumption. So S_2 and S_1 obviously have the same material consumption coefficient. So you can see here M1.5, M1.5, but we break it out in this table by the product variable name S_1 and S_2, again, for when we build our dictionaries later, so that we have all the appropriate keys for building our decision variables and constraints. Next is the DF unit rate table. Similar to what we've done before, we do a merge here between the DF unit rate and the DF product so that we can get the linkage between the unit, the product, the period, and the rate. So this table, again, has all of the units, all the products that you can make on those units, the periods in which we have to consider each of these, which again is all 4 periods, and then the specific rate. So even though, again, this is time invariant, we're just creating this value coefficient for each set of unit, product, and period. Finally, we have our DF unit capacity. No data transformations, we read this in directly. So we get the unit, the time, and the period. And so again, you can see here FD1, FD2, as we mentioned before, they're going to be shut down in period 4. So we have no time available on those processes. And then we have our DF purchase table, which is, we talked about before, represents the material that we can buy from which supplier at what maximum availability and price and in what period. And as noted before, the only real change here, most of this is time invariant, but we will not have any material 3 available from supplier B in period 4. So now that we've brought in our data and we've done the necessary transformations in order to construct the temporal data dictionaries that we're going to use to build our decision variables and constraints, we can move on to building those specific parameters as we've done in the past with some dictionaries. So we create some lists here that we're going to use for looping through and generating keys in these different dictionaries. One thing you'll notice is this will be very similar to what was done in previous episodes, except for the nesting of these dictionaries is going to be one extra layer deep, because now we have to also include time periods. So the first one is the x sub ij parameter, right? So this one is time invariant, so there's no nesting with the time periods, but we do create a dictionary for each product, the coefficient of consumption for each material. And so when we do this, I'm going to rerun this whole thing just to make sure everything comes out appropriately. So when we do that, we get our dictionary X, which again is our variables, our production variables. So product F in premium market tier 1, F in premium or discount market tier 2, and then the materials consumed and the coefficients. So this is similar to what we've done in episode 3.3. It's time invariant. The next one that we create is our opening inventory dictionary. So this is going to be essentially the on-hand material that we start with in inventory, which we got from our materials table. That's pretty straightforward. We have our material and then the opening inventory, 150 and 100 for materials 1 and 2, 0 for material 3, and 150 for materials through 4. We make another dictionary V, which again is going to be we'll use this to create upper bounds on the inventory variable. So this is the maximum amount of inventory that we can have on hand at any given moment for any of these materials, 1, 2, 3, or 4. We now have our P. So going back up here, this is the profit. So this is again going to be P sub NI, the profit of product I in period N. So here we do have to create the nesting for the period. So we create first a period key. So Pn is going to be periods 1, 2, 3, and 4. And then we populate that for each product. S underscore 1, S underscore 2, F underscore 1, F underscore 2, and then their specific price information here. So we create that first layer of the dictionary, and then within that, we create another layer and assign based on the period and the variable name, and then we assign the price. So that ends up looking like this. Periods 1, 2, 3, 4 is the primary or first level key. And then second nested keys are the specific products in that period and the price of those products in that period. And we go through and do something similar for each of these. I'm not going to go through each of these because it's very similar code. But what you end up with down here are all your parameters. So D for each period, 1, 2, 3, 4, the maximum demand available for each of these different products. Into each so again, F underscore 1, F underscore 2, 15 and 50 is the maximum demand. We created a time variant dictionary and parameter, even though the data itself is static, just again for simplicity and illustration. R and T, so again, the rate that we make each of these products on each machine. T, which is also time variant, so the amount of production time on each machine in each period, 1, 2, 3, or 4. B and C, which are time invariant parameters we covered earlier. R, which is a time variant parameter. So this is the cost or the price of purchased materials from each supplier. So we've got 3 layers of nesting. We've got periods 1, 2, 3, 4. Then we've got the material, and then we've got the supplier and the price. Again, for material 3, we have 2 suppliers, A or B, have different price. And then A is similar to R, except instead of price, this is the availability. So we, again, nested by period, material, and supplier, and then the actual tons of each of these materials that is available for being purchased. So now we're ready to build and solve this model. So step 1 is, again, creating our model object or problem objects. Still calling this production resourcing, and we're specifying this as a maximization problem. Step 2, we're going to create our decision variables. So the first thing that we do is, in order to create these, is we create these indices. We've covered this in past episodes, but for this product index, we're actually going to be creating three elements in each index, which is going to be how we create our Y sub NIK variables. So we need to have N the period, I the product, and of course the unit rate. What we're going to use that in order to get the unit, so we get K. So that's what the product index is. We do something similar for the byproduct index, which is just the period and the material. And then we also need a raw material index, which is going to be, again, the period and the material J and the supplier S. So this is the NJS index, which we'll use for like the Q sub NJS amount of material that we purchase in each period from each supplier. So that's what that index is for. And then we also make a material index, which is just going to represent the materials that we have at the facility in each specific period. So we're going to have an index that's basically material and for period and material. So we create these indices and then we use them with the LP variable.ditch method for pulp to create these. So Y sub NIK, again, is the amount of material I produced on machine K in period N. And we're going to create a variable for a period, product, and equipment for each period, product, and equipment in product index. Lower bound is 0, since we know we can't have negative production, and these are continuous variables. Similarly, for the byproduct, we're going to have the period and the byproduct, and we loop through the byproduct index for each period and byproduct in this index. Lower bound 0, continuous variable. Q, which is again Q sub NJS, so this is the amount of material J from supplier S purchased in period N. So we're going to have Q, and then we're going to make one for each period material supplier for period material supplier in the raw material index that we made up here, the raw index. Again, lower bound of 0, category continuous. And then for each of these, we're going to go ahead and update the upper bound. So as you recall, we have this dictionary up here, A. And so what we want to do is loop through each of these decision variables and use the NJS subscripts to key the dictionary for period, material, and supplier, and add these material availability upper bounds to the decision variable. And so we do that for each Q.item. So each decision variable Q, we're going to look up. It's a little complicated to read here, but each of these is a specific key in that dictionary. So I00, I01, which again is Q, the decision variable, and I02 are the subscripts we need to key this dictionary properly and get that upper bound applied. So then we do that here. M, again, if you recall, M is going to represent the decision variable for our inventory change. So whether we draw or build inventory for a specific material in a specific period. So we have M, and then for each period and material for period materials and that index, the material index we made earlier. Lower bound is none. So I mentioned earlier that this has to be allowed to be negative to represent an inventory draw or positive to represent an inventory build. It's a continuous variable. And then finally, we have our inventory variable I, which like M is going to be created for each period and material. So for period material in that index, it does have a lower bound of 0 and it's also continuous. So those are all our decision variables, and then we can see and inspect each of those here to make sure they're created correctly. So we have essentially here are decision variables for all of our products, S_2, S_1, M3, F_2, and F_1 for all the pieces of equipment that you can make those products on and for each period. So you can see here we have a lot more decision variables than we've had in past episodes. W is also looks to be created correctly. So we have a decision variable for each period, 1, 2, 3, 4, and the amount of byproduct B1 that will be made in each of those periods. Q, the amount of material purchased. So you can see here, this also looks correct. We have one set of decision variables for each period, 1, 2, 3, 4. For each materials, 1, 2, 3, 3, and 4. And we have 2 for 3 because we have 2 different suppliers, A and B, for material 3. So that looks correct. M also looks correct. We have, again, inventory draw or inventory build decision variables, M sub NJ, for each material, 1, 2, 3, and 4, and each period, 1, 2, 3, and 4. Similarly, I looks the same as M, which it should. And now we have, this is just some code that does not need to be here. Now that we have created and reviewed the decision variables, I want to draw attention to the fact that compared to previous episodes, we have significantly more decision variables. It'll be much harder to make sense of the results if we're not careful about how we store and structure the decision variable data. The code shown currently is new, and I want to briefly cover its purpose. Unlike previous episodes, I'm going to create a preliminary data frame that I will later populate with the solution results. The preliminary data frame will allow me to create keys or indices over which I can perform aggregation, and that will help with data visualization, all leading to easier analysis of the results. What I'm doing here in the code is creating a list of variable classes called var classes, a list of variable class names called var names, and a dictionary of the indices or subscripts assigned to each variable class for the mathematical model. Using these, I will create an empty data frame with columns for each index or subscript, which will be populated for each decision variable. To demonstrate how this works, let's take the first example for the production variable class y. So for I in var classes, the first one is y, and we're going to check for each of these classes whether or not their index or indices fall within one specific case. For y sub ik, we're going to say var named j, which is initially 0, which is y, and we're going to use that to find the appropriate index in this dictionary. So using this first element y, we'll get npk, and this condition will end up being true. Once we find the correct case, depending on the type of variable class, we're going to take the keys from that variable class and put them into a list called initial list, or ini underscore list. This list is actually going to be a nested list. So for y, we're going to have a list for each of these keys. So the first element in that list will be for s underscore 2 rx2. Once we have that initial list, we're going to also create an empty dictionary. And then we're going to populate this dictionary as follows. For the first element, for the first sub-element in each element of the initial list, we're going to extract that into a list called t period, because we know that the first element is period. We're going to create a list called t period and then make it create a dictionary and key that off of period with each of these initial periods. So we'll have a dictionary period, and then we'll have these first elements in that dictionary. And then we're going to do that for the variable name and for the process or equipment. So we do it down here for the product or the product variable name, and then we do that here for the equipment. And then we also want to get the name of that variable as well, which is going to be this string here. Once we create this dictionary, we're going to actually append this dictionary. Oh, sorry, and the last thing we do is we indicate the type of variable. So this will just be, again, the type of variable class, so y, w, q, m, or I. Once we create this dictionary, we're going to append it to the df var data frame we created up here. And when we append it, it's going to append it to the appropriate column. And we'll do that for each variable class. And so the end result looks like this. We have a data frame right now with 96 rows, because we have 96 decision variables, and 8 columns representing all the possible indices that we use for all of these different decision variables. So for the first class, which is our y sub nik, the production decision variables, we have the name, and then we've extracted each of these indices into the appropriate column. So period, product, and equipment. And since this type of decision variable class does not have a byproduct, material, or supplier index, these are going to be left blank. Similarly, down here, you can see our decision variable class I for inventory does not have anything for product, equipment, or byproduct, but period and material. So at the end of this solution, we're going to have new columns here for the values and the reduced costs for each of these decision variables. And then we'll be able to use this with various types of data visualization tools, whether it's Power BI, Tableau, or Spotfire, to help expedite and make more clear the analysis of results. So that we can now move on to the remainder of the mathematical model, which is creating the objective function and adding the constraints. So for the objective function, we add each of the terms I covered earlier. This first term is going to be the profit contribution for each of the different products we're making on each machine or in each period, multiplied by their respective price for each period and each product, and we're going to sum that up. We're going to do the same thing for the cost of each byproduct that we generate in each period, and of course, we're also going to include the cost of all the raw materials we're purchasing from each of the different suppliers at the various costs. Now, one thing to note here is the sign convention. So in the data file, I put the costs of the raw materials in as a positive value. So in order for this negative contribute to be a negative contribution, I have to maintain this negative sign here. So whatever your convention, just make sure you're consistent when you're constructing the objective function. And then I add this objective function to the model. And now for the last step in constructing our model, we'll go through the various constraints. Now, these will be obviously more complicated than previous episodes because we're having to create constraints for each period as well. So you'll see a general theme here is that we have to do all of the constructions we did in previous episodes for material balances, but across each of the different periods. So here, as we've done in previous episodes, we're creating the material balance, which on the left-hand side of this is going to be the total, the sum of all of our production for product P on each machine K in a given time period N multiplied by the consumption coefficient for each material for that given product. And we're going to sum that all up over each product in each machine. And that has to be less than or equal to the inventory draw for that material M in a given period M, plus any of the material we're consuming that's made in an upstream process, plus anything we consume, or sorry, anything we purchase or procure from a vendor. So again, total consumption of material M has to be less than or equal to any change in inventory, plus any upstream production, plus anything that we procure or buy from a vendor. And then like past episodes, we name these. So material balance underscore string N, which is going to indicate the time period for which this constraint exists, and then string M for the material. So we name it by material balance, the type of constraint, the period, and the material. And then we are going to loop through each period 1, 2, 3, and 4 to create the correct number of constraints. For inventory balance, very similarly, we're going to do this for each M in material. So for each material, we're going to create a specific inventory balance. Now, you'll notice here that I actually have 2 sections of code. So this first one is because I actually have to create a distinct constraint using the dictionary I sub O, which is the opening inventory inputs that we had from our data file. So just for this first period, I have I N equal to 1, period 1, and material M has to be equal to our opening inventory, minus whatever inventory change, whether that's a draw or a build, that happens in period 1 for material M. So this is how we have to construct this just for the first period. For subsequent periods, so I look at periods 1 plus N, so this would be periods 2, 3, and 4. For each of those, I can use this same code, but I can loop through the index and I can have I sub NM is equal to I sub N minus 1M minus M sub NM, which again is going to give me the inventory balance for each period. But since N, if I were to have, say, N equal to 1 here, I would not have a I sub 0M, which is why we create this up here. Production time balance. So again, similarly, we're looking here and saying that we're going to take all of our production, Y sub NPK, for a given product on a machine in a given time period N, divided by the rates that we produce that product P on that machine K. And we're going to sum that up for all the products made on a given machine K in a given time period N. And that has to be less than or equal to the total time available for that machine or process K in that period N. And again, we name it production time, period, machine. We do the same thing for our material balance, where we define how much byproduct we're making for all the different products that we're making in a period N across all different products and all different equipment. And then that's going to be the yield, or what we get for our W sub NB variable, which is the total byproduct made in a given period. And again, looping through each period. And then here we have our product upper bound, which again, for each period is the maximum demand that we can realize or that we can supply for a given product, whether that's S_1, S_2, F_1, or F_2. So again, for each period, we're going to take the total amount of product we're making, Y sub NPK, across all machines that make that product, gives us the total amount of product that we're making, whether it's on mixer 1 or 2, and that has to be less than or equal to the total available demand for that product P in a given time period. And we name this constraint as well, max product underscore time period underscore product name or product type. And so that's how we build these constraints. And as I've covered in previous videos, I want to check this. I'm going to write this model, and then I'm going to check it to make sure that it looks like it was built correctly. Now, admittedly, I will say that this method of checking is going to become not very effective when you start to get really big models where you have, thousands or tens of thousands of variables, because reading that would be nearly impossible. But it is still good to maybe spot check within those files of 1 or 2 constraints or 1 or 2 1 or 2 bounds to make sure that everything's being constructed properly. And so here I can see my objective function. It looks good. I've got my Q decision variables here multiplied by the prices, right? 3 or 5 or 2. So generally speaking, it looks appropriate that I have all of my Qs for all of my materials and all my time periods here with the negative value. So this is going to be a deduction against profit. I also have my W times the coefficient, which is the price coefficient, right? The negative 0.01 cost for the byproduct. And I have that for each of my time periods. So generally speaking, that looks correct. And then if you review these, which I have, but I won't go through, you have all of your products for each market, whether it's tier 1 or 2, and each time period. So the objective function looks correct. And then we can spot check a couple of these constraints to make sure they are also built properly. So we can go ahead and check a material balance. For material 1 and period 1, we see that we've got our inventory change variable plus our purchase variable, which is correct. So moved over to the left-hand side here, since we have a less than or equal to 0, so they're negative, which is correct, plus whatever we're consuming here, which is again the decision variables for production of that product on each piece of equipment that makes it, but only for time period 1. So it looks like that's done correctly. And that plus these has to be less than or equal to 0. And we don't make any, we have no upstream production for material 1, so we don't see any other contribution here to the availability side. So this looks correct. And then we can just double check that this is also replicated for future periods. So we come down here, we can see material balance in period 2 for M1 looks the same, except for the period indices. So overall, this looks like everything was built properly, but I won't go through all of this for the sake of time. So coming back to this, we can see that we move on to solving the model after we've checked the LP. We get an optimal solution, which is good. We get an objective value of $18,481. And now I'm ready to go ahead and extract the results or the values from our solution and put those into the data frame I created earlier. So this code is basically the same that I've had in previous episodes to extract all the values from the pulp object. But what I'm going to end up doing here at the bottom is once I create the data frame for the variable results, I'm going to merge it with the other data frame that I created earlier, df_var. I'm going to do an inner join, and I'm going to do this on the variable name. And so what you see here is the data frame I had before, 96 rows. The first 8 columns that I had before, plus now I've merged on the value and the reduced cost for that. So again, the value is whether or not I made any of this material on this mixer in this period, what the inventory was for this material in that period, and then the reduced cost associated with that. And so as you can imagine, as I mentioned earlier, 96 rows trying to go through this and make sense of all of the decision variable values is going to be somewhat difficult. So that's why we create this, because we're going to move on at the end of this code review. We're going to move on to a business insights dashboard in Power BI and look at some of the results there. So the constraints, I did not do something similar with the constraints that I did with the decision variables. So we just have the somewhat difficult to look at results for the constraints themselves. But you could do something similar for the constraint classes as well, where you could create additional columns here so that you could have the indices for the period and the material, or the period and the product type. So you could do something similar there, but for the sake of time, I did not do that. So with this, I'm going to pause here and move over to the Power BI dashboard so that we can look at the results and try and see if we can gain any insights into what the solver gave us. All right, so just to wrap this video up, I'm going to very briefly go over this Microsoft Power BI file. And really what I'm trying to show here is how you can use these data visualization tools to help with solution analysis when you start to get bigger and more complex models. The visualizations here are very basic. It's not something you would expect to see in a sort of professional environment, but I made them very quickly just to illustrate the point I made earlier in the episode about how you design your data structures to store your results. So in this file, I have 4 tabs. The first tab focuses on sort of material inventory and purchases across all 4 time periods. The second tab is for looking at your production on for various products on various processes or equipment. And then I've got 2 real simple tables for constraints and variables in these 2 tabs. But we're going to start with this material tab. And if you recall from the problem definition in period 4, both our flashing units for producing material 3 are shut down in the final period, so there's no production capacity. And our material 3 purchases are constrained because our supplier B in period 4 is unavailable. And so I want to just show quickly how you can use this visualization to sort of assess the impact of these constraints. So first, as you can see, it's pretty simple. I have a stack bar chart here, first, second, third, and fourth period of the model. Up here, I've got 3 filters, which are just directly off of that data frame I created in Python and exported to Excel. So this first filter is just the type of variable cost we're looking at. So in this case, inventory currently. And then we can slice this graph off for material type or supplier. So on the type, I'm starting with inventory and I'm looking at all materials and suppliers. And you can see that for materials 1, 2, and 4, which are the blue and purples, we're basically drawing those inventories down across the first 3 periods and then consuming them completely in period 4. For material 3, though, we see a slightly different behavior. So if we were to just slice by material 3, we see that we're actually building material 3 inventory in periods 1, 2, and 3 to a pretty high level, and then consuming all of that in period 4, so we have no remaining inventory. So that is all driven by the constraints that we impose, shutting down the flashing units in the final period, the final week, and then also constraining any sort of additional purchases for material 3 and period 4. So we can also now see the impact that those have on inventory. So we're building inventory to make sure we can conduct some production in period 4. We can also look at what we did with material purchases. So you can see that we're purchasing material in all 4 periods. We have a big spike in period 3. So if we slice this down by supplier, we can see that we're purchasing all 8 tons from supplier A for material 3 in all 4 periods. For material B, we're only making a purchase in the 3rd period. So, basically the way you can read into this is that in periods 1 and 2, we're buying the lower cost material 3 from supplier A, and we're producing material 3 from our 2 flashing units, which are up and running. In period 3, we're also purchasing the 8 tons from supplier A. We're also maximizing production from the flashing units. But because in period 4, both those flashing units are down and the 8 tons from supplier A is insufficient, we're making a decision in period 3 to purchase additional materials, 14.8 tons from supplier B, since we won't have that ability in period 4. So again, real quick, you can kind of assess how these different constraints and bounds that we're placing in these adjacent periods are affecting decisions made in other periods. And so that's really basically the example I wanted to walk through. You could sit here and do, sort of more analysis on the product tab if you wanted to, see how much production you're making by specific pieces of equipment, or specifically, how much production you're making in total for a given product. So for example, if you wanted to get your total F material, your total fuel additive material, you could select both of these, and then that gives you your total fuel production, or sorry, fuel additive production over all 4 periods. We're not making any fuel additive for the secondary market, only for the primary market. And similarly, you could do the same for your solvent base. Here we can see we're making 75 tons of solvent base in periods 1, 2, and 3, but in period 4, we're only making 35, likely constrained by material availability. And then in these tables, you could sort and filter as well to try and identify any specific constraints that you want to look at. So again, very simplistic, but again, big complex models with thousands or tens of thousands of constraints and decision variables require something of this sort in order to do your solution analysis. So that concludes this episode and the series. Thanks again, and we look forward to seeing you for the next episode.